Hi there, students. This is Dr. John, your physics and math professor. Today we're going to be looking at converging lenses. And we're going to contrast this to what we did previously with converging mirrors. I've made two little sketches here for you. I've made a little tiny sketch of a converging mirror. I've just put these in here. I'm going to erase these later. And here are the converging lens. Now, if you notice here in the mirror, things come this way. This is an object. It'll come this way and it'll reflect right here. This spot right here is the focal point. In other words, light focuses right there, and this is a mirror. There's a wall over here. That's the little sketch marks that I have there. So light can't come to this side. You would not expect it to come to this side. You would expect light to reflect to this side, and since the light is coming to this side and focusing on this side, this distance here, the focal length, is positive. It might be +5 or whatever. This is a positive number. Why? Because light is all coming together there, and it's coming together at the side of the mirror where light should be. Now, if you look over here at a lens, this is just a little sketch of a lens. Here again is an object very similar to that. But notice here, light comes through the lens and it focuses at that spot here. Now, you would think for a lens, light should go through it. That's what it should do. And if the spot where the light focuses right here, that's the focal point, which is where light should focus. If it does focus there, that is a focal point, and that is a positive distance. It is a positive distance because it's on the side of the lens where light should be. It's where light should focus. So notice here, this is a converging lens, and this is a converging mirror, but the real spot where it focuses is on the right side here. It's on the other side because light should go through a lens, but it's on the reflective side because light should reflect from a mirror. For these optics questions, if you just constantly think of what should light do, for example, for a mirror, light should reflect onto that side, and if it focuses over there, it's a positive distance, and this would be a real image over here if there's an image on this side. And on this side, images should occur on this side, so if it hits here, this is a positive focal length, and positive images or real images would form on this side here as well. Now, you may notice something else. The mirror here is concave. That is, as light comes into it, it's like it's coming into a cave. But for a lens, a converging lens is convex. That is, when the light comes here to that side, just think of that side there because this is symmetrical to both sides. Light can't come into the cave, it's sort of vexed. Hence the word convex. That's how I help to remember it. So light can't come into the cave here, it's vexed. So, but this is a convex lens, but it's also a converging lens, converging mirror. They are different. This is concave, this is convex. Just remember the difference. Otherwise, these two are completely parallel to each other, except the images that are real are on this side for a mirror, and the images that are real are on this side for a lens. Now, this time I'm going to take a look at this big picture that I drew at the top here, and we're going to go over that and give you some expansion on that. In this lens over here, I have drawn all the possible locations for the different objects, and I've drawn all the possible locations for the different images. I have put real images in red, and I put these beautiful brown color here to be the virtual images. And these three different regions here, I've drawn this way here. Region number 1, I've marked here with an orange, and I've expanded on that right here. Region number 2, which is basically the center of curvature up to the focal length, I've marked as Region 2, I've expanded that over here. And Region 3, which is inside the focal length, I've expanded that over here. And just to remind you from stuff we've done in previous videos, the center of curvature would be the center where you would draw the curve of this outside of the lens. Now, often for lenses, we'll put a F and a C on both sides. F, typically for thin lenses and thin mirrors, is half the distance from the center here to the center of curvature. Half that distance would be the distance to the focal point. The same on this side. So we'll often draw these on this side as well, because remember, we could come from either side. I'm just drawing this from this side because that's the way it's conventionally done. If you had put all these objects on this side, all the images would of course be on this side, just like that, just completely reflected or flipped around, like you're looking at this from the other side of the board. Now, if you want more help with this, check out my website. I also have downloads there for you, study sheets like this that will get you all of this information where we have converging mirrors, converging lenses, all on one sheet that's easy for you to download. It's completely free. You don't need to register anything. I want to be the go-to place for high school physics and math students. You won't get help like this anywhere else, for sure not for free. So come to my website and hopefully we can help you to be a much better student. Now let's get back to this video by looking at region number 1. Here in region number 1, I'm taking these two images that are beyond C, beyond the center of curvature, drawing them over here, and I've drawn two lines. Normally in ray diagrams, we'll draw two lines from, say we often start with a head. The arrow would be the upward part. Say a man is standing there, a person standing there. This would be their head, their body, their feet. The arrow is just to show the direction. This would be the principal axis, and then we will draw lines parallel to that. And if we measure something, the height of an object above the principal axis, that would be a positive height. If we measure something below, like over here, the distance below, this would be a negative height, just like it should be, just like you would expect. So let's take a look at these two objects here that I've drawn in dark green. Let's take this object number 2 here. I've labeled them here, and I've also labeled over here, I've labeled the images over here. So take this one, number 2, we'll go this way, and then we hit the lens here, and we come in and hit the focal point, and we continue on, and then we'll draw the second line. The second line would be this brown here, where you go through the center of the lens. Now that's a difference as well. For a mirror, you go through the center of curvature. For a lens, you go through the center of the lens, because the center of the lens doesn't diverge the light at all. It's basically so thin that it's completely flat there, right there in the middle. So this brown one comes through here and hits over here. Notice it hits over here, and where those two, where the green one and the brown one hit, we have an image. This is an upside down image. I've drawn it red. It's a real image. Why is it a real image? Because it's on the side where light should go. You would tend to think lenses should let light through, and they would form images on this side. And since it does that, it's a real image. That's just your way to remember it, and hopefully that helps you to remember it much better. Now notice here these two images here. For image number 2, I already went over that. Image number 1 is further away yet. We still take the same ray. It's exactly the same light green ray that comes down here. And then I've drawn this orange ray that comes through the center. And notice it meets here. As your object gets further and further away, notice that your image gets closer and closer toward this. This would be F right here. And this would be C. It gets closer and closer to F. And notice because of this green line here, it would get smaller and smaller. So if you had very, very far away, your image would be very tiny over here like that. And eventually it would disappear. As your object would go to infinity, your image would disappear right there. It becomes infinitely tiny. So this is this first region here, region number 1, which takes you up to the center point. Now let's go here to region number 2, where we're going to start on the center, and we're going to start moving toward F. Things get a little bit more interesting. I've redrawn these exact 3 points here, and I've labeled them as well. Here's the objects, and then I've labeled the associated images. Because there's so many lines on there, it might be a little bit confusing to follow them. Again, the main line comes in here, and it goes down like this. And then the other lines, here's the brown one, the beautiful brown one on number 1, goes through the center, comes over here and hits here. You'll notice that if the object is at the center, it actually forms an upside down, real image right on the center. You can see this from the diagram here. You could also see this from the optics formula here. Remember, 1 over F is equal to 1 over object plus 1 over image. Now if, let's say our focal length is 5, so if we make this 5 here, and if our object is 10, because it's going to be double that length, we could make this, instead of 1/5, we could make this 2/10. So if this is 2/10 equals 1/10, this also has to be equal to 1/10, which means the image also has to be equal to 10. And the image is a positive distance. Why? Because we measure positive distance with lenses going in the direction that light should go. Light should go through the lens, so we measure positive distance for the image on this side. So hence that would be a positive distance. Now let's take a look at a couple of other of these points. Point number 2, again, we'll follow this, and it's the orange line. We'll go right to the center and form an image here. Notice as we get closer to F, it's still upside down, but the image gets bigger. And here we're getting closer to F again with 3. The image gets much bigger. As you're getting closer and closer to F, this image will continue to get bigger. You can notice this line over here, this green line over here, that will continue to expand. This red one will continue to get bigger and bigger. Actually, you could never reach F, because as you get closer and closer to F, this real image will go to infinity. You can sort of see that from the diagram. I'm going to show you a quick sketch about that. But first of all, let me show you again from this optics formula. 1 over F is equal to 1 over object plus 1 over image. Now if our focal length is 5, like we just had, that it'll be whatever it is in your problem, and you place the object at 5, notice 1 over 5 already equals 1 over 5 here. So that means this here has to equal 0. The only way to do that is if the image goes to infinity. So that has to go to infinity that way. I'm going to show you that too with a quick sketch. Okay, let's say we put a point right here, and that's another object right there. Notice this green line, the light green one, would still be exactly the same, but the other one would go through the center here. What do? Take a black one here, and I would go straight through the center like this. I don't want to mess up all the other lines, and it would continue on like that. It's not, my diagram isn't perfectly accurate, but if you drew this very accurate, this black line here that would go through the center would be parallel to the other, this light green, the lime green line, so that these 2 points will never touch. We always draw the image where the 2 lines, the one that goes through the focal point and the other one that goes to the center of the lens, where they touch. And where they touch is where the top of the head of the image is. But notice in this case, these 2 lines are parallel. They will go to infinity and they will never touch. So now let's go over here to region number 3, which is where these points, these objects, are inside the focal point. I've drawn 2 objects here. Here I've drawn 3 green objects. Hopefully that doesn't make it more confusing. There's a lot of lines here. That's because everything happens on that side of the lens in this case. First we have the line that comes straight across. Since they all have the same height, this would come straight across, and then it would come down toward the focal point right here. But we can also draw, you can always draw a backward line, sort of an imaginary line or a virtual line. You do the same thing for mirrors, you can do as you do for lenses there. So that would be one of our points. And now let's say, take this point inside here. This one right here, I put a little black top on that so you can see it a little bit better. And we take the orange line that goes this way. It's going to go through the center and it's going to continue on. It's going to continue on actually that way. I don't know if you can see or not, but the green one goes this way. This one, orange one, goes this way. They will actually diverge from each other. They don't actually touch. So if we go backwards with that same one, and we take this orange one and we go backwards, notice that the green one, the lime green one, and the orange one touch right there. So that's actually the image, or it's a virtual image, because the actual rays of light don't touch there. But if we take the rays of light backwards, almost like they appear to be coming from here, going this way, from this spot right here. They seem to be diverging from this spot right here. They're not actually coming from here, but that's a virtual image. And why do we know it's virtual? Because light should go through a lens and form images on this side. If it forms images on the wrong side of the lens, they're virtual. That's an easy way to remember it. So this one here, if you got closer and closer to the lens, the image would actually start to shrink from this green line here, and you would get closer and closer to the same height as the object. Now we'll go in this direction. Number 2 here, we could do the same thing with the lines. We'd end up over here. Notice it's getting much bigger. It's expanding in this direction. And this green line here will show how they expand. Number 3, I'm starting to approach the focal point here, and the lime green one will be the same. And the other one is this purple one. Goes through the center, goes backwards. It's way over here. Notice that as we come closer and closer to the focal point from this side, that is from the inside of the focal point, the image goes to infinity, but it goes to positive infinity. It's a virtual image now, and it goes to infinity. Over here we had the image, as we got closer and closer to F in this direction, it became a negative or a real image, and it went to infinity. So it's sort of like the opposite sides of the scale. One way to remember that is if you were trying to graph 1 over x. 1 over x would graph something like this. On the positive side, as you get bigger and bigger x value, your y value would go to 0, because this becomes infinite in the bottom, which makes this 0 here. But as you get closer and closer to x this way, the y value blows up. And the same thing over here, only here it's negative. If you have a negative x, your y is going to always be negative, but it's going to blow up. So notice as you get closer and closer to this disallowed value, which is x, from the one side, you blow up to become a positive infinity. From the other side, you blow up to become a negative infinity. And that's exactly the same thing that happens over here. As we approach the focal point from this side, you blow up and become a negative infinite image. As you approach the focal point from this side, you blow up and become a positive or a virtual infinite image. You can also see that in this original diagram over here. Take a look at the tops of all of these objects. They're all the same height, which means the top of the line, that one that's completely parallel to the principal axis, will hit right here. And then what will it do? It will go this way, hit the focal point, and continue on going there. But if you went backwards with that, it would do this. I drew it a little bit away from the other points so we don't overlap there. Notice how this line here that would come this way through the focal point, which is it's the side on the real, where you have the real images, is the heads of all of these things hits that line and it goes to infinity. As you go in the other direction, the heads of the images, the virtual images, also hit that line and that goes to infinity as well. So I hope that helped with the converging lens. I'll have other videos for diverging lenses and mirrors. Check those out. And remember to like and subscribe to this video. That's what helps me to make more videos. And share this with all your friends too. I will see you in the next video. Bye-bye.